Parallel circuit lab. Here we go. Create the circuit shown at the right. So 2 batteries going this direction, positive, negative, 2 batteries, a switch, and 2 light bulbs in parallel. I made them in series. Well, that was silly, but I'll do this quickly enough. Okay, so there's one. Now I could put a wires across there. I guess I could do that real quickly. Make sure I have an extra wire here. Actually, that's going to slow me down. Here. There's a wire there. Actually, let's do this. Boom. 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 Boom helps. All right, so there it is. Now notice it goes through here. It'll go through the switch. At this point, it will split. Some of it will go that way, some of it will go this way, but it's still a wire. So it will split and go through the 2 and join. These are called junctions. Okay, so let's follow what it happens here. These are branches, the left branch and the right branch. Close the switch to ensure the circuit is working. Ta-da! To test that the light bulbs are indeed in parallel, unscrew one of them. Aha! Hopefully you remember. I should have done this earlier, but since I had them set up that way. Do you remember when we had them in series? It bears doing this, so let's just do this very, very quickly. So here they are in series. I unscrew one, they both go off because there's only one path for the electricity to flow. Anywhere in that circuit that I take apart, I make a break, it'll be an open circuit and it won't flow. But if they're in parallel, this is the easiest way to tell if something's in parallel or in series, is that if you unscrew one, the other one stays on. Okay, likewise if I do this, okay, or this one, okay. Now I can't undo this one because that's for both of them. That's part of the main circuit, okay. So now, if the other light bulb stays on, they're in parallel. Both of them go off, they're in series, you need to fix your circuit. Is your house wired in series or in parallel? It's in parallel, good Lord. Imagine if it was in series, you turn off one thing, so you turn, or I just can say they're independent objects, independent, wow, spelling's hard, independent circuits. Like you don't turn off your light, the light in the kitchen and the lights in the bedroom go off, okay? Everything that you have in your house is wired in parallel so that things are independent. Otherwise, wow, that would just be crazy and crazy weird. Make the circuit at the left, putting a potentiometer in one branch only. Okay, so let's see if I can pull this off. So here, I may need another wire to get this to work. So I have a wire. This one goes all the way over here. Oh, I just so happen to have another switch that'll work just ducky. Okay, so that is now a wire because I have it closed. All right, so now, okay, go ahead and turn it on. Oh, that one's on. Now this one's on. So notice that the potentiometer, or the variable resistor, is affecting only one of the light bulbs. Okay, let's go ahead and read what it says here. Adjust the potentiometer. How does the potentiometer affect the current in branch 1? It changes it. How does the potentiometer affect the current in branch 2? Doesn't. Okay, write a statement about branches in a parallel circuit. Go ahead and pause and write some statement about branches in a parallel circuit. Okay, I'm assuming that you did that. One last chance to pause and do that. You really need to write things down. Okay, so the branches in a parallel circuit are independent. Now notice, I don't have to write fancy or write complete sentences here. This is just for learning. Now resistors in parallel, well, we have R1, R2, and R3. Those are the 3 resistors that we had before. Let me get those together. I've got the resistors now, but let's just make a quick comment. You'll notice that all of these have a switch in them, and you might wonder why I always have switches. More switches. Most of you may not know what that is. It's from Mel Brooks. Anyway, so, or it might be Monty Python. Oh no, I feel terrible. Okay, so the reason that I have switches is so that students can easily turn off the circuit. When I first started teaching, one teacher didn't use switches in her circuits, and she was going through batteries like every day, and my batteries were lasting weeks. So if you're a teacher, use a switch in any circuit. So we want R1 to be the smallest, so this one will be the green one. the blue one, and the red one. Okay, so this will be blue, green, green. And remember, the green was 5 ohms, and this is 10 ohms. And number 3 was, why did I put them, now they're in reverse? Well, that was just dumb. I'll rewrite that. So this one is red, and that's 20 ohms, right? Okay, so here we go. So I'm going to put the green one, the smallest resistor, and I think actually this would be better if I put the bigger resistor first, but let's see what happens, okay? So, okay, there you go. You see some light, no big deal. So now I'm going to put the 10 ohm resistor, the blue one, over the top of it. So you see how the electricity here can go through either of them. Electricity can go anywhere on this circuit, or on a conductor. It can go through the blue one, or it can go through the green one. Okay, there, now you can see the two of them. Watch. This is gonna, let's try it with there. Notice it got a little bit brighter, okay? And what happened, the light bulb got brighter. So now let's go ahead and put the red one on. Hopefully this will be obvious. Ready? That may not be obvious to you guys at home, okay? But it gets slightly brighter. Let me try this a different way. Let's put the red one, or let me see, let's put the green one and then the red one, okay? It got a little bit brighter. How about I start with a big one? Let's try that. So I put the big one, red, and notice you can't see anything. That's part of the reason I didn't do that. So now I'm going to put the blue one in there, and it gets brighter. Now I put the green one on there, and it gets brighter. So with each one that I put on, it gets brighter, okay? And why is that? Well, you've got more paths for the electricity to flow. With the green one, let me go ahead and take this off just so I can save batteries. With the green one, that's a big hole. You said, but it's a small resistor. Yeah, think about a big hole as a big hole is a small resistor because it lets a lot of water through. A small hole is a big resistor because it doesn't let a lot of water through, okay? Hold on, let me go get something, I'll show that to you. Now let's imagine we've got, these are wires, okay? So I have 3 wires here. This would be the smallest wire and the largest wire, obviously. This one, let me get them over where you can see them better. I think you can see that there, okay. So this one would be the smallest resistor because it lets through the most current. This would be a medium-sized resistor, and this would be the biggest resistor. A lot of resistance, small resistance. This would be like the green resistor. It lets through a lot of current. This would be the blue resistor. It lets through some current. This would be the large resistor because it doesn't let through very much current. Now, if you have this small resistor and a lot of current's flowing through, and then I add this one to it, now more current is going through. And even though this doesn't let a lot of current through, it still adds a little bit more. Another way to think about this, superhighway, an avenue, and maybe a side street. So a lot of people won't be taking that in comparison to the freeway, but a few will sneak through. So a large resistor does increase the current, and increasing current decreases resistance. So let's see what this does here. Let's answer the questions. Do resistors in parallel increase or decrease the total resistance? They decrease because there's more paths. That's, we're supposed to say more. Wow, moth. That's important, everybody. Moth, more paths. So more current. All right. Set your multimeter to 20 volts. With a switch closed, measure the voltage across each resistor. Okay, let's go ahead and put these in here. Now, unfortunately, because they're all kind of tied together here, let's see if I can actually get some wires here so we can try to do this here. And I don't have another spot for this one, so I'm just going to put it there. Put it there. And let's go ahead and show you what I'm doing for voltage on the voltmeter. Hopefully you can see what's going on there. Volt is over here. It says 20 volt, and it has a line that's straight. The straight line means DC current. If it's a wavy line like over here is AC current. I'm going to put it on 20 volts DC. I want this to be in COM, which is common, and a V for volts. Okay, so now let's measure the voltage. Okay, let's measure the voltage on each one of these. So this is the positive side. It's the closest side to the battery. So I'm going to measure way over here. And oh, better close it. That was dumb. So this reads 87. Way over here reads 0.87, and way over here reads 0.86. So very, very close, but those are basically 0.86, 0.86. They all read the same. Now, that should make sense. Well, I mean, it may not make sense to you right now, but let's go back and remind ourselves about something we did in our last lab, that if you have a wire, there was no change of voltage across a wire. So since you have a wire here, if the voltage here is 8 volts, the voltage here must be 8 volts, 8 volts, 8 volts, 8 volts. Wires are equal potential surfaces, or a surface that doesn't change voltage. Okay, so with the switch closed, measures the voltage across each one, and we got 0.86, and that was volts. How does the voltage across each resistor compare? They are equal, or the same, or no change, whatever you want to put there. Current in parallel circuits. This actually one is not going to work perfectly, but let's go ahead and do it, okay? Let me go ahead and pause and get it set up a little bit better. Okay, now I have them so that they're a little bit, they look more independent now. It really doesn't make a big difference. And this one, I need to change this out real quickly. I need these to connect back. Yeah, because this needs to be the total current. So let's look at what happens. Voltage goes this, or current goes this direction, just like it's flowing through a pipe, pretending that's closed. And at this point, some of it can go this way and the rest of it can go this way. And here it splits as well. Okay, and remembering that there's no change of voltage across a wire. Wires are equal potential surfaces. Once it goes through here, connects, connects. So this right here will have the total current, total current, total current, just the current through the red, just the current through the blue, just the current through the green. This one will have the current for just these. Let's see how this works out. So let's, now remember, for an ammeter, you have to break the circuit in each of these places. So let's go ahead and find the current in the different places. So current 1 apparently is over here in the green. So I'm going to do this, drop the light. You can see there's a little bit of, there's light going on there. There will be more as soon as I touch it. Now I'm going to put this on 100 so I need this in 10 amps. See over there it says 10 amps, okay? And because 10 amps is going to be less likely to blow the fuse. Okay, so goes into the positive, and I get 0.17. I get 0.17 amps. And number 2, which is right here. I don't want to touch anything to cause it, so I'm going to need to go for between these two places. Oh, no, that's the total, isn't it? So, yeah, that's not going to work. I need to take off, for instance, here. So, from this point to this point. And notice, when I touch this, it will connect the circuit. The light bulb is getting brighter. And that's 0.08, 0.07, or 0.08. Which isn't that like half? That makes sense. Twice the resistance, half the current. And then I can go between these two places. 0.03. We might want to do that with milliamps. I'm going to go back and do these with milliamps just to see if it's, so this one is milliamps. Let me turn that off while I'm doing this. Let's try milliamps, which is right there. Okay, so once again, with the green one, I get, oh, light on, duh. So I get milliamps. Why am I not getting anything? Let me pause here and figure out what's going on. Okay, so let's I made a mistake here. I think that the 200 milliamps maybe has a blown fuse. So let's just stay with the 10 amps. I need to move the lead back over to 10 amps here, right? It was volts here now, or milliamps, amps. So Let me disconnect here for a 4, which is between the light bulb and the battery. Light bulb and battery, and I get 0.3 or 0.31. And then A5 is up here, which I can do right at the switch. Positive at the positive side. 0.3, very good. Did the light come on? Yes, it did. So notice that the ammeter is allowing the current to go through. All right, so let me turn this off. That's turned off, and let's answer some questions and do the analysis. How does the branch through the light bulbs relate to the current in the 3 branches? So current in the current through the light bulb. Okay, so the light bulb, so here we get 17 plus 3, which is 20, plus 0.08, which is 28. That's pretty close, okay? Almost the same. It should be the same, but it's not. We'll talk about that in a second. Are any currents equal and why? Well, weren't 4 and 5? A4 equals A5. That's supposed to be a 5. That's kind of like moth. 5. Same path. And if it's the same path, then it must be the same current. Now, by the way, let's talk about some seriousness here. Seriously, let's talk about some seriousness. This right here, why is it that the currents do not all equal each other? And the reason is, each one of these, even though you think that 20 ohms is a big resistor, it is such a small resistor. And this has resistance. The ohmmeter itself, the ammeter itself is very, very small resistance, but it has some. If we were actually to put 4 different ammeters in this circuit at the same time, then this one would equal those 3. I have a demo for that I'm going to ask you to watch next on a parallel circuit demo. And I actually have all of the ammeters at the same time. So I will tell you, if you had the ammeters in each one of these, equal ammeters and so forth, then this statement would be true. Everybody write what you think the statement should say. Pause and do that, please. Assuming that you pause. Here we go. Current in the branches add up to the total current. So this one, and this one will all add up. So let's just make up easy numbers. That's the biggest resistor. We'll say that that's 1 amp, 2 amps, 4 amps, because this one was half the size. 4 plus 2 is 6. The total should be 7 amps. This should be 7 amps, and this should be 7 amps. Okay, let's move on to the back page. Measuring resistors in parallel. I'm trying to move this up here to where you can see. That shows ohms, so that's where I'm going to put the red one. The black one stays on common. Can you see that? It says common. But I'm going to want to move this to 200, 200 or 2000. I'm going to use let's try 200 and see if that works. If that might be too much, might be too sensitive. You know, I'm a sensitive guy, but we don't want to get too sensitive. And again, OL means off limit. When I connect them, it should read 0, which says no resistance. Well, that's interesting, isn't it? It reads 4 ohms, which means that these leads might have some resistance in them. That's going to mess things up. Let me go ahead and change these leads out. Actually, let me move this over to 2000 and see what it reads. We'll try the 2000. Okay, that was very interesting. Now, I know that you did these in the other lab, and you know that should be 5, 10, and 20. Let's just be sure. Do you notice that they are not connected to a battery? So just the green reads 4. I was hoping for 5, but it says 4. It's hard to write. 4 ohms. Please put your units. The blue one, 10 ohms. And number 3, or the red one, 20 ohms. Okay, connect 1 and 2 in parallel. So now 1 and 2 are connected in parallel. Okay, they're connected. So I could go from here to here, but I can just go from here to here because they're connected. Notice it reads 3 ohms. Okay? That's less than 4 ohms. Remember how if you have another hole, you're reducing the current. Now I put all 3 of them together, and it reads, notice it jumped between 2 and 3. Let's just put it on 200 and see what happens here. So let's see the 2 of them together. Read 3.7. With the red one reads 3.3, which is less. I'm just going to put 3.3, and it was like 3.7, I believe. Okay, but notice by adding the red one, it brought down the total. The total resistance, because when you have more paths for the electricity, you have more. You have the ability for more current, which is less resistance. Now it says here, 3 resistors are placed in parallel. A 30, a 20, and a 10. Sorry, 30, 10, and a 20. Without using a calculator, which of the following must be the total resistance? Well, it can't be 60 because that's adding them together. That's in series. 15 is greater than the 10. Notice it must be B, because the total resistance in parallel has to be less than the smallest resistor. Remember, you have a big hole, that's the smallest resistor. You add anything to it, you have decreased the resistance more than that. So if you had a 20 ohm resistor and that was your R least, that's your smallest resistor. If you put them in series, it'll increase. You put them in parallel, it will decrease. In this next section, I actually changed it up. You can use the CPO, these colored resistors, but it's hard because the resistors are so small, and sometimes your ammeter won't read it correctly. So what we're going to do instead, I've got 150 ohm resistors here. So one of them is 150 ohms in this case. I have some others, 100 ohms, etc. I'll show you that one in a second. So if I put 2 of them, let's find out what 2 of them equals. So watch. So if I put 150 ohms, close enough. I put 2, 75. Can you see that? Let me make sure I can see. Okay, so if I put 2 of them, 75. And you might be able to see what that is very quickly. This is 150 ohms, 150 ohms. What about 3 of them? 150, 150 ohms, 150 ohms. Let's do 3 of them together. You get 50 ohms. Huh. So hopefully you're seeing that this is 150 divided by 1, 150 divided by 2, 150 divided by 3. Now, 150 divided by 4, I'm not as good to do that in my brain, but notice it went down. 150 divided by 5, 30. That's perfect, right? Now let's get some numbers that are super easy for all of them, okay? Now, as long as all these are connected well, these are each 100 ohm resistors, and let's see if the pattern still holds. Hopefully you can see that over there very well. So one of them should equal around 100. Okay, 2 of them should equal around 50. 3 of them should be around 33. 4 should be 25. And 5 should be 20. Well, howdy doody. How did that work out? Just nice. Now this last section wants me to compare a series and a parallel circuit. You will notice here that I do not have a battery. My reason for that is I don't know that these batteries are the same. If I just throw in a battery, this one might be weaker than the other one. So I want to use the same battery for this, even though, yes, the other parts are not the same. If I wanted to do this correctly, I would use the same device and then I would redo them. Actually, let's just do that real quickly. That won't be that hard. So here's the parallel circuit, and I want to know the total current going through the parallel circuit. Okay, so I'm going to take, I know this is not going to be a lot of current, but I'm going to put this on 10 amps over here at 10 amps. And this has to move over to the 10 amp setting. This is going to be very, this one won't be as small. The series one will be very small. So I go ahead and touch across here. The light bulb will come on. No, oh, there it is. Barely comes on because I only have one battery. And there's 0.2 amps. Now, by the way, this is 200 milliamps. If this were in milliamps instead of amps, that might actually blow the fuse. So it's good that I'm in milliamps. So the parallel circuit, pull this down here. The parallel circuit was 0.2 amps. Okay, now let's see the series circuit. I need to make these in series real quickly. I just turned off my voltmeter to save power in the voltmeter because those take time to replace. Using the same circuit elements minus some wires. But you know that wires have very little resistance. All right, and by the way, when I turn this one on, notice there's no light. That's, beforehand it was what, 3 ohms, 3.3 ohms. Now it's 20 plus 10 plus 5, so that's 35 ohms, plus whatever the light bulb is. So now let's put this down to 10 amps. Let's see what we get. .03. Turn this off. I don't have to turn that off because it's not connected. Says, which circuit draws more current? The parallel. The answer is Y. You can either say less resistance or more paths for current. All right, so we've now just done parallel circuits, and we have seen that resistors in parallel decrease the resistance and increase the current. By the way, how you actually calculate these, there's another worksheet that will show you how to do that. We also saw that they're independent paths, and we saw that the voltage across each one is equal. So here are the things you need to know about a parallel circuit. The voltage across parallel devices is the same, but they are independent. Okay?